Stefania will talk, as you see, on deep learning-based reduced order modeling for cardiac electrophysiology. Thank you, Stefania.
Here I am.
You don't see. All
Yeah.
right, good. Now we see you.
Okay, thank you for the introduction, Alfio. And the work I'm going to present is in collaboration with Andrea Manzoni, Luca Dede, and Alfio Quarteroni, and has been developed within the iHEART project. Oh, sorry. Okay, first of all, the motivation at the basis of this work. We are interested in solving a full order model expressed as a parameterized dynamical system. This may arise from the same discretization of PDEs like the boson domain or the bidomain equations. Solving the form in two contexts, real-time and multi-query applications, entails prohibitive computational costs when the dimension of the form is large. Model order reduction or reduced order modeling aims at replacing the form by a reduced order model showing a much lower complexity. And the most used approach to ROM is the linear one, which reveals results to be ill-suited to problems featuring traveling wave behavior or problems which were characterized by a solution manifold with a very low regularity with respect to the parameters of the problem. Motivated by this, we move to nonlinear reduced order modeling. Linear ROMs looks for an approximation of the low-dimensional parameterized dynamical system called ROM, expressed by a linear combination of basis function. And pod-Galerkin ROMs are an example of linear ROMs. In this case, the matrix V is computed through proper orthogonal decomposition, which exploit the SVD of the snapshot matrix. Then the matrix P is computed, where P is a dot selection through a suitable hyperreduction strategy, which allows a testing time to assemble the operators of the ROM without relying on the high-dimensional arrays. Then the Galerkin projection, the assembling of the ROM and its solution are performed. Pod-Galerkin ROMs show several limitations when dealing with the coherent structures which propagate over time. For example, the linear superimposition of modes results in a very high-dimensional linear trial manifold, or the number of basis function needs to be very high in order to get an acceptable accuracy. Moreover, evaluating the ROM requires to solve a dynamical system which might be unstable unless you choose a time step very small. The ROM must also account for the dynamics of the gating variable, even if one is interested only in the transmembrane potential. In order to overcome this limitation, we build a deep learning-based reduced order model. In particular, it looks for an approximation defined in terms of a nonlinear function, which is the decoder function of a convolutional autoencoder. Then, for the description of the reduced dynamics onto the nonlinear trial manifold, we rely on a deep feed-forward neural network, which directly models the relationship between the parameter instance, and the intrinsic coordinates. Finally, in order to get a better accuracy confirmed by experimental results, we also add the encoder function of the autoencoder. Here I show the architecture of DL ROM used at training time. In particular, it consists of 3 blocks, A, B, and C. The form solution here enters block A, which is the encoder function, and it outputs a low-dimensional representation of the form solution. The same parameter instance associated to the form enters block B, the deep feed-forward neural network, and outputs the intrinsic coordinates. Then the error between the two low-dimensional vectors is accumulated. The intrinsic coordinate enters block C, the decoder, and it outputs the ROM approximation, and the reconstruction error between the approximation and the form is computed. Regarding instead the testing phase, the architecture is the one into the red box where we discard the encoder function. The first numerical test I want to show is a 2D figure of 8 reentry solution of the monodomain equation discretized by means of P1 finite elements. The comparison between the form and the DL-ROM solution for a testing parameter instance is the one into the movie. In particular here, the parameters is the y coordinate of the center of the second stimulus. Indeed, we apply the S1, S2 protocol in order to induce the reentry. We start from a form dimension almost equal to 66,000, and we end up with a reduced dimension equal to 5, which is very closer to the intrinsic dimension of the problem, in this case to 1 parameter and time. In the picture here, we show the trend of the relative error over the testing set versus the CPU time, both for the DL-ROM and the Pod-Galerkin-ROM at testing time. And it's evident, it's clear that the DL-ROM outperforms the Pod-Galerkin-ROM both in accuracy and in efficiency. Then we increase the complexity of the problem by considering both reentry and no-reentry dynamics. This was achieved by enlarging the dimension of the parameter space. Here I show the ROM dimensions and the testing time for the DL-ROM and the Pod-Galerkin-ROM. And here the deep learning-based technique allows us to achieve a speed up almost equal to 25. Then we perform an error analysis where the error is the one shown in the slide. And by fixing a testing parameter instance and looking for the distribution of the error over time. This distribution is almost uniform, and the maximum error is associated to the first time instance, which is the most different over the parameter space. Then we repeat this analysis, but this time by fixing the time instance and by looking at the distribution of the error over the parameter space. This error is always lower than the 1%, except for the testing parameter instance associated to the interface between the reentry and the no-reentry range. Now I want to highlight some of the benefits introduced by the use of the DL-ROM. Its dimension can be kept very small. Indeed, it can be kept very close or even equal to the intrinsic dimension of the problem. By directly modeling the relationship between the parameters and the intrinsic coordinates, the DL-ROM can be queried at any time instant without requiring the solution of a dynamical system until that time. For example, if we are interested in computing the ROM approximation at testing time at the final time, here we get a speed up, the DL-ROM speed up are about 607 or 7,000 times faster than the Pod-Galerkin-ROM and the FOM. Moreover, the time resolution required by the DL-ROM can be chosen to be larger with respect to the one required by the numerical solution of dynamical system associated to EP. The DL-ROM, moreover, avoid to use expensive hyperreduction techniques to deal with terms that depends non-linearly on the solution or on the input parameters. And as I said, it doesn't require to account for the dynamics of the gating variable. The drawback is that the DL-ROM depends on n, which is the form dimension, and it may lead to longer training times when this dimension is large. I want to highlight that this may appear as the computational bottleneck of this technique, but the higher training times are always justified by the efficiency introduced at testing times. But in order to overcome this issue, we extended the DL-ROM to the pod-DL-ROM version, in which the goal is to approximate this time the intrinsic coordinates V transpose U, where we exploit this time the randomized SVD. The per example loss function becomes the one in the slide. Then we apply the pod-DL-ROM on both physiological and pathological EP. In A, the parameters are the coordinates of the center of the scar, which moves over the domain. The deep learning-based techniques allows to achieve a very fast, very efficient testing time. With testing time, I refer to the time needed to compute NT. In this case, NT is 1000 time instance for a testing parameter instance. Moreover, the pod-DL-ROM technique allows us to drastically reduce the training time. Then we analyze the use of pre-training on a test case in which we vary the conductivity in the fibers and in the fibers direction and transversally. Pre-training is a form of transfer learning consisting in training a model to solve a simpler task and use it as a starting point to train the model on a more complex task. In practice, we use the optimal weights and biases found on a simpler task as initializer for the network on the more complex task. We use pre-training in two scenarios. First, by increasing the foam dimension starting from n equal to 4096. And the use of pre-training allows to further reduce the training computational times from 38 minutes to 5 minutes, or from 32 minutes to 12 minutes. Then we use pre-training also by enlarging the parameter space, and with the use of pre-training, we again decrease the training times from 31 minutes to 16. Then we move to physiological EP on the zygote template left ventricle geometry and on a needleized left atrium. Here, the conductivity tensor has the definition as in the slide, where the conductivity in the fibrous direction is the parameter. The foam and the NPOD dimension are the one in the slide. In both cases, we match the intrinsic dimension of the problem, which is 2. And I want to remark the times. In particular, the use of the pod-DL-ROM technique decrease again drastically the training times from 28 hours, which is the training time of the pod-Galerkin ROM, to 39 minutes. Regarding instead testing time, we are able to achieve real-time results. Indeed, the testing time is slightly smaller than the physical duration of the phenomenon. And here again, for the left atrium, we have 0.2, which is equal to the physical duration of the propagation. As in the previous case, the atrium, the solution on the atrium was found by solving the bidomain equations, which are discretized by means of isogeometric analysis. In the case I show here in the slide, the parameters are the coordinates of the center of the second stimulus, which vary over the fuchsia region. We start from a foam dimension almost equal to 150,000. We operate a first dimensionality reduction through the randomized SVD, and NPOD is set equal to 256, and then we end up with a reduced dimension equal to 20. In the slide, I show the activation maps for two testing parameter instance in order to highlight the ability of the pod-DL-ROM solution in replacing the foam one when evaluating output of interest. Moreover, the pod-DL-ROM technique is able to accurately capture the variability of the solution over the region, which is quite large. And this is remarked highlighted by the shape of the control lines which change over the parameter space, indicating that the direction of propagation of the front change over the parameter space. Finally, we trained the network in 5 hours, and for the testing time, we again achieve real-time results. So concluding, the pod-DL-ROM approach allows us to overcome the main computational bottleneck of the DL-ROM technique, which is related to the long training times when the form dimension is large. But the pod-DL-ROM neural technique also inherits all the features of the DL-ROM technique, which in this way it's able to achieve a very efficient testing time, even faster than the real-time solutions. Moreover, thanks to suitable pre-training, it's possible to combine multi-fidelity models. With this, I mean different spatial discretization or different physical laws in order to further enhance the training times. And finally, this approach has revealed to be robust because we successfully applied it to a vast class of problems, including structural elastodynamics and fluid dynamics. Here in the final slide, I show the papers related to the presentation of today and also the GitHub link to my account for the code of the DL-ROM technique. And thank you for the attention.
Thank you, Stefania, for your very interesting talk, for being on time. I'd like to ask if there is any question for Stefania. So maybe I have one. How do you choose the ANN? How much freedom do you have in choosing ANN? How are the final results robust with respect to a change of ANN, say, or is there improvement possible depending upon the way you choose the ANN?
With choosing the ANN, you refer to the, I don't know, to the convolutional or the feed-forward nature of the network, or refer to the hyperparameters tuning with this, I mean, the number of layers, the number of neurons?
The first one, indeed.
The first one, okay, the first one is related to the fact that we are replacing the map of, for example, in pod-Galerkin ROM, the matrix V, which maps the low-dimensional coordinates to the high-dimensional one. And autoencoders does the exactly same things, but in a nonlinear way, okay? And regarding the deep feed-forward neural network, I also tried with LSTM neural networks, which takes into account the time structures of the solution, but I achieve better results with the DFNN, which moreover allows us to query the solution at any time instance without having a time structures behind.
Okay, thank you. So there is still time for a quick question, if any.
There is a question in the chat.
Okay.
Okay.
See it.
I was wondering.
So I'd like to ask how long one of your simulations take to complete.
No, I guess it's the final one. I was wondering how applicable are the DL-ROM and pod-DL-ROM techniques for learning the dynamics associated with spatial heterogeneity in conductivity and/or ionic properties. Yeah, Okay, this is a very preliminary results, but here, while modeling the scar, you are indeed changing the conductivity tensor by setting equal to 0 it with respect, well, in correspondence of the scar region. And I didn't try to other type of heterogeneity, but this is a work in progress, and I guess that it can be very applicable and very interesting to do it. The unique thing you might to take into account, if you have a special distribution here, you probably have to change the network, because here you will have, I guess, a tensor in input, and probably you have to change this network to a convolutional neural network.
Okay. So I guess we have to stop here. Thank you again, Stefania, for your very interesting talk.